Please, Ricardo, the floor is yours.
Okay. First thing, I'm sort of an imposter here. I'm actually a scientist of a detection of gravitational waves and not of nuclear energy. Here I'm in the temple of nuclear energy. And so I feel a little bit like an imposter. So what I'm going to do, because I'm actually proud of what we do with gravitational waves, I'm going to tell you in 3 view graphs where does the uranium come from? And so let's see, does it move? Oh, here. So if you take a large star, something like 10 to 20 solar masses, our sun burns hydrogen into helium, and then it will stop close to that and just make a dwarf white star. In another 5 billion years, there is plenty of time. But the large stars burn much faster, and the first burn hydrogen into helium, then from helium they go out to all the other materials until the last one that they can burn is iron. And at the end of the lifetime of everything, when most of the fuel is burned, the iron will fall down to the center of the star, and then when it reaches 1.5 solar masses, it just collapses into a neutron star. The core collapses into a neutron star, and by doing that, it emits a large amount of gamma rays and the neutrinos that push out the rest of the star, and what you get is a supernova. And so all of these atoms, from hydrogen to iron and a little bit above, get spewed out in the galactic gases atmosphere. There is a little bit of that, and seed it, and then the next generation of stars will be enriched with this material. And in fact, the Sun is the 4th generation star. It came much later into the history of the galaxy, and so that there was enough material to make the planets, heavy materials. However, there is something interesting here. When you burn, you can rivers only go downstream. When you burn, you can only, the stars can only go down and get around iron. You can get a little bit up during the shock wave of the supernovas, but it's a mystery on how you could arrive to make lead, uranium, gold. Okay. And we actually found the answer with gravitational waves, because what is happening here, okay, is when you have 2 neutron stars that come together, eventually they inspire, and eventually they make a black hole. And as they inspire to make the black hole, the outside part, the end output for the ballerina effect, try to go faster than light, which is not possible. And so what happens? You throw out all of these 4, 5%, up to 10% of the mass is thrown out in the surrounding space. And this matter has to go, these are mostly neutrons, it has to go up the gravitational well of a black hole, so it slows down and cools down. And these neutrons start connecting together. And because there are no protons to repel each other, they will actually connect and glow, and you can see they are growing here. They become heavier and heavier. Uranium is down here. So they become heavier and heavier. These are only neutrons, and now the neutron will start decay into protons in time, and they go and populate the actual Mendeleev table there, and then they decay down here. Then they will, the one that are heavier than uranium will decay rapidly. The last one to decay will be probably plutonium, that takes tens of thousands of years. And then you get with the Mendeleev table. What we found is we found an event like this, because of Virgo, which is the Italian gravitational wave observatory that I helped design, the jet mechanics, and the two in Lagrange, the United States, where I worked for 12 years, we could point at that, in that direction, at that distance, just at about at the same time that Fermi satellites saw a gamma ray burst coming from that region, and everybody pointed scopes in that direction. And what they found what is called a kilonova. They found the fluorescence of the heavy metals. Okay. And so what we found is the galactic gold factories and uranium factories and all of that. I couldn't resist showing this to you, but then what we do, we have the uranium in a fission, and then with neutron, we break it in two parts, and then you get some like 200 MeV of energy coming down this fission. And we do it on many neutrons, and we can make actually energy. So rapidly, mostly for the first front row here, this is how is a third generation nuclear reactor works. You have a number of bars made of plutonium containing uranium. They are in water. And then you put enough of those that the neutron emitted from one is caught by the others, and every time that you hit a nucleon, you produce 2 or 3 more neutrons, and that is called a chain reaction. And by doing this, you deposit all of that energy into the water, which is the moderator of this reactor, and the water boils, and then you use the steam to run a turbine and make electricity out of that. Obviously, in this the reactors that are around now, they are all large. They produce between 1 and 1.5 gigawatt electric, which means that they are between 3 and 4.5 gigawatt thermal, because of a Carnot cycle and the Carnot tax that you have to pay in order to go from heat to energy. And so these are now, they have a large steel containment vessel, and then you have a concrete containment building. Both of them were missing in Chernobyl, and that's why there was a big problem there. And now I'm talking, now there is a lot of talk about the 4th generation nuclear reactors. The 4th generation nuclear reactors are, the big difference is that they are built in a factory and then they are moved to the place where they have to work. Okay, what's happening here? Check this. And so that is the main thing. There are many kinds of those, and I'm not going to talk about because I'm ignorant and because there are too many. But the idea is they are smaller, they are modular, they're built in a factory, they are installed supposedly fast. And some of them are intrinsically safe, some other get safety in different ways. And I'm only talking about the ultra-safe neutral modular reactors made by the ultra-safe nuclear company, because are the only one that I'm talking about, that I know something about. These are small reactors. They are about 3 meters in diameter, something like 6 meters tall. They live inside a well that is maybe 15 square meters. And then there is a pump that circulates helium to extract the heat from here. Then there is a heat exchanger, and then you bring the heat outside for any use that you may want to do. So why are they ultra safe? There are 5 physical reasons, okay, that are there that you cannot avoid. Okay, the first is they have a self-arresting feature that many reactors have. In our case, due to the concentration of uranium-238 and the geometry, means that if we design them to work at, for example, at 900 centigrades, and you let it, you overheat by 300, just only 300 centigrades, due to the Doppler effect, the uranium-238 absorbs more neutrons and stop the chain reaction. Okay, so if you have more temperature, there is more absorption, and there is a point in which the reactor stops. So we define, we put the density of uranium-235 into our moderator, which is graphite, so that it works. For example, it gives out 30 megawatts at 900 centigrades. And then if it, for whatever reason, like for example, if you stop cooling, putting cooling into the system, then the reactor stops and stay hot, but there is no nuclear reaction anymore. And that means that if I make it work, for example, at 1000 centigrade, when we will not do this immediately, we go to either 600 or 900, then the maximum that it can overheat is 1300. But the entire geometry of the core is all ceramic, and there is nothing that damages or get damaged below 2350 centigrades, and so there is no way that this reactor can self-damage. If you later on, you will be able to come down and see this is a piece of graphite, a piece of reactor. This one is one of the fuel cartridges that you see in the drawing there that fit right in the holes. There are several thousands in there, and you can actually see some cut ceramics, and we go into it. We discuss how these work. And also all the decay product and uranium and plutonium and decay product are confined in these that are called the chrysoparticles, but then are trapped inside these cartridges. Okay, and they are confined in a way that there is no conceivable accident in which a radionuclide, except tritium, which comes out that can come out of it. This is unstable. Maybe I should use it works. No, this one is off. Then it's not water cooled. Yes, switch it on and I'll use that one. Okay, is it okay? Works. All right. Okay. If we the heat extraction and cooling is made with the flow of helium into the reactor run by a pump. Essentially, it looks like a jet engine here that pumps at high speed helium into it. So it's helium cooled, and we eliminate the water, and therefore we eliminate the cause of steam explosion. If you overheat the water, then it generates high pressure of steam that then blows up your reactor, and that is what happened, for example, at Chernobyl. And then after there was no containment, so after the explosion, then it caught fire, and that lasted for a long time. People my age remember, unfortunately. And you also eliminate the possibility of generating hydrogen and oxygen. That is what happened at Fukushima. That was a much lesser problem, but still a problem, but a much lesser problem. And that is what blew up the cover, the outside cover, not the containment building, but just the outside, the crane cover was destroyed that way. And the last point is that these things are small. We make them intentionally small. They have 50 megawatt thermal, which is about 1% of one of the big reactors. And and also they have a lot of thermal inertia compared with the big reactors. So they are ultra safe. How are they built? Well, they are, this one is a progression. So if we first start to make price of particles, that I will show you in a moment, that are about 1 millimeter in diameter. When you will come and see, you can see that there are thousands inside here. This is a cutout. Yeah. And the core is uranium, and then there are shielding outside. They go inside these 3D printed cups, okay? And then by chemical deposition, we infiltrate silicon carbide in the cartridge to fill up all the voids, and then you end up with a cartridge this way, which is protected by a minimum of 2 millimeters of silicon carbide outside. This one is not as hard as diamond, but gets close to it, and so you have this cartridge. And it goes into these hexagonal modules, of which I saw out at least to bring it to you, so you can see nuclear grade graphite. Yesterday I was in Malone, where they build this sort of graphite. They did it for other reactors, and number of 37 of this graphite make one floor. And there are something 4 or 5 floors into a reactor. The total is about 4 meters. And so this one is the core of the reactor, and this goes into a pressure cooker that works at 30 atmospheres. And then there is a wall on this side, concrete wall. There is a neutron shield, and then already inside the tank, and then a wall outside there. And then outside here, there is a turbo pump that circulates the coolant to extract the heat. The coolant is helium. And then out here, there is a flow of molten salts, the same that are used on solar plants, the concentrated solar plants. And so how is it built? So now this assembly, I took out the pressure cooker, took out the neutron shield. This one is a neutron reflector made out of graphite. And the yellow, the blue is hexagon here, and then inside there are all these cartridges, and inside the cartridges there are all the beads I was telling you. So that is how the reactor is built. Okay, and how do you extract the heat? Well, there is a flow of helium that goes on the outside of this pipe, and go outside the reactor, then comes down into the reactor and come back into the center of the reactor, back to the turbine. There is a way, either an electric motor or a primary turbine that makes it rotate. And then there is an heat exchanger, which is very small, because at high temperature you can make heat exchanger very small. And then here are the pipes that bring out the heat to the user. And all of this is about 50 square meters. It's a small apartment, and the area, this is a bit taller than an apartment, maybe 3 floors. And it all, we like to put it underground because it makes it more protected. So this is the price of particle. And it was developed in the 50s and 60s to make airplane propulsion. They wanted to have airplanes that stay up there full of loaded of nuclear bombs, of course, but they failed because they did not have this technology, the technology of 3D printing of cartridges of fuel. And it's all built with, I will show you, with refractory material, of which the first thing that melts is the core of uranium dioxide at 2350. And outside there are first a layer of soft activated carbon, the same that you use in the Brita carab to take out the impurities and drink better water. And that one is a layer in which any decay product gets stored into, okay? And then there are two layers. One of the pyrolytic graphite is different from this one, is extruded graphite. And pyrolytic graphite means that you have gases, essentially methane, that get heated and broken down by radio frequency, and the atoms of carbon deposit on these beads that are floating on a fluidized bed. And so you grow this graphite in a glassy form, which is very impervious to diffusion. And much more, then you go to another chamber in which you develop the last layer of silicon carbide, that is this same material here. And that one is very impervious to any decay product, except, as I say, tritium, that is not built in large quantities in a fusion, into a fission reactor. But if you have it, you can actually harvest it and sell it to the fusion people because they need it. You just find the gas into a helium flow, and all you have to do is separate it. So that one is the size of it, which is 0.5 millimeter in diameter. So the entire thing here is the size of a poppy seed. Okay, so this is 0.5 millimeter diameter. This one is the low density carbon to store all the volatile fission to decay products. And then these are the two sealing layers that I told you. And now you will see how we make them. You can see these beads are floating. There is an upflow of gas, and then it's very hot because we put it into a very powerful microwave oven for the microwave to dissociate the gases. And you can see here they are coming out in production. This production line, this one is on test, but the production line is operative in this moment in Tennessee. In Oak Ridge in Tennessee. And then there is the cartridges. The cartridges are 3D printed, as I have shown to you, like this. This one is still fragile because it's not infiltrated. When you 3D print, you have a structure. Some of you have been 3D printing with plastic. You can see that it is still the structure of what you do. Then when the gas infiltrates in and deposits the silicon carbide in all the interstices, it becomes solid and impervious to all diffusion of decay products. And there is much more protection. Already the 35 microns that you have on the beads, on the size of beads would be sufficient. But here you have 2 millimeters of silicon carbide, which is a formidable barrier forever. And it's this one, what I have here, I've been cheating you. Instead of uranium dioxide, we put plutonium dioxide so I can bring them on the plane. But if you put uranium here, it will be very heavy. You could use it as a bullet to go into tanks. To break them because it's very heavy and very strong. Incidentally, silicon carbide, you have seen some photos of these tanks that have these plates in front, these bricks in front. And this one is typically silicon carbide, and they added to the tank later on. The tank is made out of steel, so that it is much harder if a projectile that hits them bounce back. Silicon carbide is used a lot as a very strong material. It gets being used more and more in industry, like the paper industry, like all sorts of things. So what you see here is a cylinder, and now you see a little slide here because I couldn't carry in my next to my computer. I couldn't carry anything bigger than that, but you can. This thing is about 100 kilos. And this one resist up to 3600 centigrades. And so these are interlocking holes. These are fuel wells. You put the fuel, and the small one are helium flow. So the helium flow through there. So this one I did anticipate to you. How does happen that uranium-238 actually has a negative, the reactor has a negative thermal reactivity. That comes because uranium-238 has a forest many lines of absorption of neutrons. Here they appear overlap, that is just a printer that has a fine, a big wall. And but they are extremely fine because the uranium has a very long lifetime, and therefore these lines are very narrow. That makes at the room temperature the absorption is very small. If you were to put them near absolute zero, the absorption would be very low. But the more you heat up, the more absorption of neutron you will have there because of the Doppler effect. The Doppler effect is what you hear when a siren passes by. Okay, that is just because a car with a siren that pass by. At the beginning, you see when it comes below you, behind you, you have a frequency that is diminished by, and then on the other side it is accelerated. In changing frequency means changing energy in a quantum world. Now, about the fission product confinement and fuel disposal, as I said, these two layers are already in normal condition. They are already sufficient to confine the material. Every decay product is stored into the coal activated carbon layer. And silicon carbide is very strong, is stable, is non-reactive, and does well. The question is why we are so sure that confinement will be essentially forever. Well, to go through this material, all of this decay product has to diffuse through. Okay, and the diffusion is an arrhenius process. And the diffusion is depth is logarithmic with time, and diffusion speed decreases exponentially with temperature. And there was an accident that happened to us, happened to the reactor with the hot shell. It's a pebble reactor that essentially have bomb shell made out of graphite with inside a triso particle, and they have something like 10,000 reactors, and then they change continuously, a couple of hundred a day. Then some of these broke down and wedged into between bigger box there, and or integer box. And so locally they made an higher density of uranium and a lower flow passing the helium flow passing by. And it took, they know that the temperature went over 1300 centigrades because they had some steel metal wire there that found completely molten, so it went above 1300. And after half a day of this, I read the report, some of decay products started to come out with the helium gas. And so from that one, we have a starting point, and then knowing that the diffusion speed comes down rapidly with temperature, or goes up rapidly if you heat, and that it is the diffusion depth is logarithmic with time, we can figure out that for anything to come out through not the 35 micron in that case, but coming out of a 2 millimeter thick shielding that is in a cartridge will take millions of years. And but that one is what I was just telling you. And so it takes millions of years geological, very long time. If you put it in rock that is not too hot, it will stay there forever. And the question is, we have to keep this material sealed inside here for 200,000 years to have a few lifetimes, or several lifetimes of a plutonium, so that after 200,000 years, the plutonium will have decayed, the radiation from plutonium will have decayed below the radiation, the decay from natural uranium. The question is, will it work? Well, we have an example that we got from the Romans, and we found some of these amphorae at the bottom of the sea that are about 2,000 years old. So they don't go at 200,000 years, but they go at 200 years old. And yet they confine wine into it and even garum. Unfortunately, the wine turned into vinegar, so they could not really taste it. They did taste it, but it was very sour. But it was confined. And this one is a very poor ceramic made out of clay and wood fire, and it does not compare with silicon carbide deposited with chemical vapor deposition, which is extremely compact and extremely hard. So we are perfectly comfortable that this cartridge will, unless you disassemble because you want to recycle the leftover fuel, which may or may not want to do, and that is very difficult to do, it will stay there for much longer than it takes to let the plutonium decay. So we are happy that our fuel is ready for disposal if you want to dispose from the day you prepare it the first time. Now, operational lifetime of detectors in the past, every year or two, you had to take out the fuel rods and reorient them into the reactors, so the one in the core that are less exposed to neutron flows, or they are more exposed to neutron flow, they burn faster, you then would put them outside. And so typically you make the reactor which has only 1% or less than 1% above criticality, so it does not run out from you. But that means that every year and a half, you have to pull out these rods and put new ones, rearrange them, etc. What you see here actually is the Cherenkov light coming out of this fuel rod. It gives you the idea that even after the reactor is switched off, there is no chain reaction there. There's only 1% of residual power coming out. They are pretty hot. And in fact, if you take them out of the water, they can catch fire and then release the material inside, which is what happened in Fukushima. Not from the reactors. Most of the 3 reactors that were closed, they had not this problem. Very little came out of those. The big release of fission products came from the rods that were in a pond next to it, or cooling pond, waiting for them to decay to a low power so you could transport them to get dry cask. And the earthquake broke the swimming pool, and the water went out. And after it took another day and a half for heating up, and then the thing came out. There is no risk to do it with these things, because even if you take them out immediately, they are perfectly happy. They will not catch fire. They are an oxide, so there is nothing that can happen to these things. So what we did, we said we don't want in our reactor to refuel it every year and a half. So what we did, we poisoned it a little bit. One of the things that we did. So inside this cartridge, we also some beads which contain boron. Boron is a poison. Is what eats neutron like crazy, and so if you have too much boron, the reactor simply does not start. So we put just a little bit of boron there, and then we add, we can add more uranium-235 in the core. And then the nice thing is that when you burn out you have a reaction, the boron then absorb one neutron just exactly as in the same proportion as the uranium-235, and so what happens is as you burn out the 235, the criticality goes down, but at the same time you are burning out the boron and criticality goes up, and if you put the right amount of boron in there, you have a stable reactor for 10 or 20 years. So that is one of the tricks that you're using. And then when you finish up the boron, there is no boron left. Then you keep using the uranium and the reactor goes down. At that point, we take the core away. And then we know that, for example, the outer of these guys burn more or less. And then in the next reactor, we put the same units in different positions, maybe alternate, and this is half burn, and we alternate with an higher concentration of uranium-235 next to it, and with more boron into the flat cartridge, so we alternate them. So these things get burned a number of times, and you burn them more and more. So we have a good efficiency in burning there. And so that is how we do it. And typically, that is what we do. Of course, economically, you want to burn it as fast as possible because you have to pay for the reactor and its uranium load at day one. And so it costs something like 80–90 million. And then you have to pay the mortgage, like on your house. So if you can pay the mortgage or use out the energy, but energy is what pays, in 10 years or in 7 years, it's much more economical than doing in 20 years. So that is just an economical reason. And so we will start with reactors that last 10 years. We can make 30 megawatts. We can make them at lower power for specific places. 15 megawatt and last 20 years. If you want to go in the Yukon up north, that is what these reactors were designed for. They were designed initially for the mines in the north of Canada, in Antarctica, in Alaska, place in which you want to put a reactor there. It just works, and it works for as long as you can. And then you don't have to go and change it very often. That's why we made it miner-proof. And it was simple. And at the time, we did not think that this could be used for general use, because at the time when this development was made, methane gas was costing $10 a megawatt of heat, and a megawatt hour of heat. And we sell it for the first cycle at $13 a megawatt hour. That is the cost that we expect to have. And so it was not competitive. Then there was the raise of price of methane, because the people started using methane to stop coal burning. And then there was the war that brought the price up. Now the price of methane this week was between $70 and $90 a megawatt hour, which made us very competitive. Then, of course, the $30 that you have at the beginning is because you have to pay for the reactor itself and for the decommissioning, so you have to store everything at the end. If you make a refuel, then it's much cheaper, because all you have to do is to change to pay for this the uranium fuel, which is much less expensive, so the price goes down by a factor of 3 to $10 a megawatt hour. And then, but back then, nobody thought about competing with methane. It was methane that became outrageously expensive, and now we can compete. So what we do now, for example, because we want to make these reactors small, if you want to have more power, you may use many of these reactors small, After all, they were built to be controlled remotely, to be over in Yukon and on a mine and be controlled from Pasadena, for example. This is like this, and then only have some operator close by or send somebody if need be. So the idea is that you put a number of these reactors, and then all of them produce a flow of hot molten salt, and then you pump all of these flows of molten salt into a container which has hot salt here and cold salt there. And then to make electricity or to make whatever use of it, you just pump this molten salt to a heat exchanger and you make steam out here. So this, for example, is a supercritical CO2 power plant designed by Hyundai with some 43% of thermal to electric efficiency, and putting out something like 200 something megawatt of electrical power using 7 or 8 reactors. The advantage is also that having a number of reactors in parallel, after 10 years, when they are worn out, you change them one at a time. You just use one a bit faster, and you don't have to stop the plant. So you have a continuity. But the other advantage is that these things are very, they deliver heat. And many industries like to use heat, ceramics, chemical, agricultural production. For example, one of our biggest, we have 3 big customers at the moment that in the United States that are ordering our reactor, and one of the biggest is in Illinois, and they use it to cook marmalade and pure tomatoes and such for the political chemistry. So this is there are all sorts of interesting uses of heat, which are much more producing salt. We have a Solvay in Wyoming, which is a second of our big customers there that use that to produce soda and so on. So the size is small and they are ultra safe. There is no, we couldn't conceive any accident. I couldn't conceive any accident before. That was when before I started working with them. I happened to be in there by an accident. The accident is my daughter married the son of a designer, which also is a good engineer. And then I started discussing. I didn't find any problem there. I dug into it. Eventually, I put 10% of my retirement fund into the company because I figured out that it was a safe bet. And they are small, they fit inside factories, and as I say, they deliver directly heat. And the important thing for industrial people is that they are reliable. There is no blackout that can happen, and you can produce your own electricity as a waste, as a byproduct, and so many industries are very interested. And the moment that they will become available, they want to install it. We are pre-sold of a number of reactors here. And the reactor number 2, for example, will replace some gas oil burner that are used to produce electrical power and to heat the campus of Urbana-Champaign University. And so these are going right inside the campus, in the middle of the students. And that tells you, and these people are not crazy. So we explain to them, they are convinced, as I'm convinced, that this is ultra safe. And you can, there is no risk in putting them in the middle of houses. So you can provide heat electricity, you can provide heat district heating, and all sorts of other things. And Well, this one I told you already. And the advantage of storing the heat into molten salt is that you can put it in here at a fixed speed. For example, here I have reactors 30 megawatts, and you have 7 of them, so I have something 200 megawatt to 210 megawatts of heat that I pump into here. But then when you have 6 p.m. peak of electrical power, you can draw the heat out of this deposit much faster speed. Go out at half a gigawatt or more, and you are only limited by the size of a turbine that you put inside there. So you can use them as peak catcher to compensate for the holes that are left by the renewable, like solar, that stop working in the afternoon, or like wind that stop working when there is no wind. So that one is useful. Or you can use the heat to, if you, for example, you want to use the renewable electricity to produce hydrogen, we can provide the heat to preheat the steam, and then you can make electrolysis with a fraction of electrical cost. We will see that in a moment. So the number of advantages, these reactors use no water. So the reactors of water, if you have boiling water, you are up to 100 or 200 centigrades because it boils. If you are pressurized, you can go to 300 and something. But if you try to go higher, the water just go into steam, and then everything blows up. But we have no water in our system. So the first 2 reactors, the 2 models that are coming out, will be at 600 and 900 centigrades. These temperatures are defined by the available molten salt chemistry. And then we can go even higher. That requires some gas exchanger, which are a bit more bulky, and we will use it. But if you have a high temperature of delivery, then you have a smaller limitation from the Carnot cycle. If you can work at the start at 150 centigrades, you want to cool down to 30, 35 centigrades in the Carnot cycle, and the turbines, which are huge, and then you need those huge cooling towers that use water to cool, and people are afraid of it, so nothing bad into it. But if you start at much higher temperature, you can afford to throw away a little bit of heat at a higher temperature, like 50, 60 centigrades, like in your car, radiator of your car. And so you can have a heat exchanger to water to air, like in your car, that are much smaller, that you can see the sign here. They're just fun, like the one in front of your radiator, and below this radiator, they occupy much less volume. And nothing wrong with the towers, but these ones are not visible, and people are afraid of those towers. So it is good. Or you can use some low temperature heat for district heating. So the high temperature you want to use to produce electricity because of the Carnot cycle. So you want to cool down, start as high as you can, and then cool down your steam to produce electricity. And then the waste, the question is if you want to throw it away or you want to use it. And and also you may have heard that when the Fall River was in a drought, they actually had to stop even some fuel powered gas and gas oil power plants, because they did not have water to cool them down, to put the waste heat into it. And this does not happen because there is always air around that we change it. So being able to run at high temperature, as the ceramic allow you to do, has a number of advantages. So you can make cheap hydrogen, we'll discuss it in a moment. Eventually, you'll be able to make steel processing. immediately, what you do, you want to use electrical ovens. That means that you do electricity, you have no tax, okay, and then you use the electricity to make high temperature ovens. You can process hydrocarbons, so you can run refineries that instead of burning methane to heat up, you use the chemical heat. But you can also do something else, because if you have hydrogen and CO2 from something, and you have power to add, you can work backwards and you can go back into methane and other gases, and from both you can go back to producing jet fuel and car fuel, and that one is green because it started from CO2 and water, and then when you burn it to your car or your jet plane, it goes back where it was. So that one is feasible, and there are people here that know how to do this chemically, as long as you can put power in heat. And then there is lots of work in polymer production. I was talking with a chemical company. They were telling me, oh, yes, we need the heat and we need things. And every time there is a 1/4 of a second glitch in the line, the one that, you know, the electrical lines, when there is a lightning that hits the line, they switch off and on again for a fraction, 1/8 of a second, 1/4 of a second, I forgot what. Every time that happens, we get a 30,000 euro damage, because the chemical flow, we have to stop it, drain it, and restart it from scratch, because even that 1/8 of the second glitch is trouble. So they are very interested to have something which is inside that does not get stopped. So we are happy that we can solve that problem. Hydrogen. Everybody talks about hydrogen, and then if you say, how do we do it? I was asking the question, how do you do hydrogen? Everybody thinks about using electricity to make electrolysis, but there is not much made, okay? And if you could make already, if you can make electrolysis instead of just room temperature water, if you can do electrolysis of high temperature atoms, high temperature steam, well, it takes much less electricity for one reason. When you heat up a molecule, the molecule moves faster and faster against and toward. They oscillate faster and faster against each other. If you overheat it too much, they self-separated. That's what happened in Fukushima. But if you stay below, let's say, at 800-900 centigrades, and you have a fuel cell that takes the temperature, then you have a gain of a factor of 3 or 4 in efficiency. So, and then you can even produce electricity together. We have a joint venture between us and SK Ecoplant and Hyundai Engineering, in which you produce the heat, and that heat is part of the heat flow goes into a turbine to make electricity, and part goes to produce superheated steam and go into this fuel cell produced by SK Ecoplant, and here comes the hydrogen there. The first plant that does this, our target, what we think we can do is 2028. But the real, there is another way that may be even more efficient, is to use a chemical process to produce hydrogen, is to go through using sulfuric acid and iodinated acid. And this chemical process, they tell me that it would be even more effective than going through electricity. However, whichever wins, they all work at temperature that we can provide. People put a lot of effort in decarbonization. Well, one of these batteries that fits on a truck has 3 million megawatt hour into it, 3 terawatt hours that is equivalent to 250,000 tons of oil, which is a full supertanker. That one is the equivalent of a full supertanker. I mean, it's almost half a kilometer long, okay, and that amount of energy for a truck produce no CO2, does not produce 3/4 of a million tons of CO2 that go into the atmosphere. It all produces a barrel of these cartridges that we actually can use 2 or 3 times, because I told you we can reburn them, and eventually we can put them down into a repository or recycle if somebody wants to spend the time and effort to recycle and put it into a fast reactor. Can you make money out of it? Footprint. Well, the aeolic has a footprint of calculated of 17 grams of CO2 per kilowatt hour electric produced, and that is the best. This comes mostly from the concrete and steel that you need to produce these huge structures. Our batteries, if you build them in normal factories, is already 11.5 grams. Conventional nuclear is smaller because they are bigger in size, but they are much bigger in power. So at the end, they produce less. However, our plan is to power our factories with our own batteries, and that brings down the footprint to even lower. So that's fine. How many do you need? Well, for example, Italy consumes 700 terawatt-hour of energy per year, okay, which is equivalent to burning 250 of these reactors per year. Of course, we are not planning to take the entire power load of Italy, because there are also other sources of energy and other reactors different from ours. However, there is not only the Italy, and so if you are burning if you were to just naively talking, okay, I want to make take the entire power requirement of Italy, I would have to build 250 batteries a year, which means once a day. It's not unthinkable of doing something like this. The cost of this is 3/4 of the cost of a Airbus 320 or of a 737, and both of them are built more than one a day in average in different factories. They are much more complex and dangerous. So it should be feasible to build up the supply line to build a reactor a day in Italy and provide this to Italy first and the rest of Europe, and then the third world, etc. You can also make desalination of water. If you have an excess of electricity built, you can ship it over to inverse osmosis plant that produce water that way, or and that one you can dispatch back to you using a water system. Or if you put these batteries near the seaside, you can use the waste heat to also produce some other drinking water. Costs, I was telling you, a reactor costs 90 million to build, because this includes the cost of the reactor, the place, and including the cost of decommissioning and disassembling everything, then disposing of. The second load it does not have these costs, it's only 30 million every load. And if you make $90 million divided by 3 million megawatt hour, makes that delivered at high temperature, which is useful, makes that it costs about $30 a megawatt hour plus interests that change from place to place, finances, costs, your mortgage. And so there are different configurations. The third reactor will go online. We are building the first production line, which is a pilot production line, which we plan to build the first reactor in 2026, 2 years from now, and install this in Canada. Because originally we wanted to send them in the northern mines of northern Canada, so they were the first in line. The second one will go down in Urbana, Illinois, and there is one that goes somewhere in Alaska, and then the next two go in Helsinki, near Helsinki in Finland. They don't have enough with the big power of the plant that they have there. And the fourth one of this certification will go in Poland. I actually am reserving for the moment the next one for Italy if the politicians that are here manage to push faster than the need that we have from the legislation and verification. And there are lots of doubts. There are people here that I know that have doubts that we can do it. Doesn't matter. We try to push for that tight time scale, and then we'll do what is feasible. And the prices. I've been asked by the president of the province of Mantova to evaluate what would happen if we were taking the Ostiglia power plant that is there, if we were to power using a number of our reactor batteries instead of using gas. Now here I made the study without carbon. This is without carbon tax at the cost of 50 euro megawatt hour. Looked yesterday, it is between 70 and 90. So the price is actually higher than this for gas. And if we have a $30 per megawatt hour, this one is the cost to power the 2 gigawatt electric with our plant. And of course, if you put the carbon tax on top, or if the gas goes higher in cost, then the difference becomes even faster, even larger. And while in the case of a nuclear plant, if the second load goes down by a large factor. And almost at the end, when I told you already this one, so I can go after how many? That one I told you already. We would have to build some one a day. Oh, it's in Italian here. That's fine. Do we have enough uranium? Well, uranium first comes mostly. Most of the uranium known comes from Australia, then it's Kazakhstan and Canada. The cost now is about $80 a kilogram. And but that is an interesting point is that if the cost goes about $250 a kilogram, then it becomes advantageous to mine it from the seawater. There is so ppm of uranium in all the water of the sea. That means that in the mines that we know, there are 8 million tons of mineable uranium, and maybe more, petrol is only know, but in the sea, 4,500 million tons of uranium that can be extracted at this price, until you deplete the sea. And because the uranium cost is low in the plant, there will be very little change. So we have enough uranium for many centuries. And then we can burn thorium, modifying things. We can use thorium, which is 10 times more of it. Okay. Now I go to space uses. Well, this one is ground uses, like I told you. This one is to go in Alaska. And so you can use the same technology to box inside here radioactive materials. Okay, and is very confines the radioactive material. But if you have a very active radioactive material, this will become very, very hot. And that you can use it to warm up a satellite so it does not freeze the electronics. Or if you have a radiothermal generator, you can produce a few watts of electricity, which is, for example, present in the Voyager that went beyond Mars, beyond Saturn now, and that's fine. Or you can make a reactor that you can put on the moon or on Mars to produce electricity. Now the reactor is big. Can you figure out what is the tough part to make if you want to make electricity over there? It's the radiator. Because on Earth, you either have water or air that you can dump the waste heat into it. It's not much water and not much air that you can use to dump the heat in the moon. So the only way that you have to do it is radiate it. That means that now your Carnot cycle, you have to have a reactor that works very hot, over 1000 centigrade, and then radiate out at 400 or 500 centigrades. So on Earth, you try to go to temperature 30, 40 degrees. In space, you have to run much hotter. So the tough part is not the reactor. The reactor is a piece of cake. Okay, I can make it over 1000 degrees or 1500. It's no problem. In fact, I want to make 1500 also for make metal, steel mills, ceramic, and such. And the next, but the radiator is the problem, okay? And the next is the space propulsion. And there are two kinds. What is shown here is a nuclear thermal propulsion. That means that you have a reactor. This one is really small. It's 1 meter in diameter, 1 meter long. And behind that, you put a very large tank, much larger than you see here, full, for example, of ammonia. You could make hydrogen, but hydrogen has a small problem, and hydrogen would be better. And then what you do, you pump this ammonia, you put a reactor up that will make a few hundred megawatts, let's say 300 megawatts, half a gigawatt, and then you pump into it ammonia as fast as needed to keep it from self-damaging, and the ammonia immediately dissociate, and then you eject the nitrogen and hydrogen outside. And because this reactor is not made with graphite or silicon carbide, it's all made with zirconium carbide, with carbide to act as a moderator. And that one can go at 3500 centigrades. And so as a result, out of a nozzle there, you can actually go there. Out of a nozzle there, you can actually have 3000 degrees hydrogen and nitrogen that has smaller atoms, and they can be faster than H2O, oxygen is heavy. And as a result, you can have twice the specific push that you can have if you burn hydrogen and oxygen. In addition, it's a nice advantage. Imagine that if you were to go from here to the moon and back, it's a fast trip. You can use hydrogen. But you remember, some of you have heard what happened to Apollo 13. What happened is the valve that was relieving the boil of hydrogen and oxygen, one of them failed, and so the tank blew up. And happily, they had some safety, some spare fuel into the lunar landing module, so with that they could come back. But if you go to Mars and you bring hydrogen, and especially hydrogen, it boils off. So you burn some hydrogen to go there,
which is very efficient because it's a small molecule at high temperature. It comes out faster and push even more than if you burn ammonia, you heat up ammonia. The problem is that when you try to come back, shit, boils off. You don't have anything to come back. Ammonia becomes a liquid at -10 centigrade. In space is you actually want to keep it a little bit warm, otherwise it may solidify. I don't know if it does or what. So you actually find it still there when you decide to come back. So you have seen while I was talking the disassembling and reassembling of this reactor, which is a beauty, and it's nice stuff. Okay. The thermal nuclear thermal reaction is good if you want to go to Mars, because you want to have a quick push, strong push, and so you push, you are in orbit, and when you are at perigee, you give a 20 minutes push as fast as possible, and then you launch to go over there. And then at arrival, you have to push back to stop, and then you have to, when you come back, you have to push to come back here, and then when you arrive to Earth, you have to push to stop again, otherwise you keep going, which is not nice. But if you want to go far, then you cannot do it with thermal propulsion anymore. If you want to go far, you have to go with what is called electrical power. Now, electrical power means that you make electricity somehow, and then you use the electricity to produce a 1,000,000 volt potential difference, and then you take your atoms of whatever, and of gas, of nitrogen, for example, and you kick it out at 1,000,000 volts, which is a temperature of many millions of centigrades correspond to. So your efficiency in pushing is maybe 100,000 times more. And so instead of using 1,000 tons of ammonia, you can use 100 kilos of nitrogen and to go and come back. In this case, what you do, you push for 6 months or 8 months, then you coast a little bit, and then when you get there, you push, counter push for a few months to stop by and get in orbit there. And you can get to Jupiter or Saturn much faster than you can do it thermal. The point again, when you do this, you can produce this power, which this time you're not trying to put 0.5 gigawatt in a short time. You want to put a megawatt of electrical power per month in a time. So you put a lot more energy into this and much more efficiency. The problem remains, which one? Same. The waste heat. So you will have to, you have a reactor that you can make a reactor that makes a few megawatt of heat, maybe at 1,000 or 1,500 or so centigrade, and then you have to radiate at a few hundred centigrades, and then maybe at that point and have a turbine in between that generates, for example, a supercritical CO2 or whatever you want to use at those high temperature, and then you can do this. But it is much tougher not to break. So it's a challenge from you wannabe nuclear engineers. But there are plenty of challenges here. There is plenty of employment, because if you produce 1 reactor a day, we also need maybe 3 new guys a day in average. No, maybe less, because most of them are remotely controlled, but we will need a number of engineers only to run it. Plus, we need very smart engineers to make a new versions of this. And I'm only talking about the micro reactors made by ultra-safe nuclear. There are many other competitors that are trying to come online.
there will be a lot of Darwinian selection. Few of them will survive, but they will be the best, of course, because that is what Darwinian selection does to you. And that's it. And now,
thank you, Riccardo, for the brilliant presentation. Now we have enough time for the question and answer session. So I will ask the floor to start with question. You inspired a lot of questions. At least on my side, but I will say just two. But before starting with my question, I would like
the
to.
modern answer is always the last.
Exactly. So please.
Yes, Laura.
So I will break the ice. About the Politecnico di Torino. You told us about tritium and the idea of separating it from helium, right?
Yeah.
And sell it again to fusion people. I'm a fusion lady, so I would be very pleased to get tritium. But there are tens of people around the world struggling to separate tritium from anything else because it is so fast in disappearing in the structures and in the materials that the risk of contamination of the secondary is there. So which are your plans to prevent any contamination of the secondary?
Yeah, the first thing, that is a tough problem, and I'm not expert in that. As I said, I'm an imposter. Yeah, I'm not an expert. I'm learning, but I come from. Anyway, we have a tritium that will come out in the helium flow. And so it is in a helium flow, so part of this flow can be passed through a cold molecular sieve. And I've done this because I was capturing hydrogen in molecular sieve in an experiment, minor experiment in Cornell when I was at lab nuclear science. So that one can be done. The question is, how much do you lose inside the materials? Well, that's a question, again, it's a diffusing problem. But it's also reasonably, at the end of a lifetime, it will diffuse through the volume. But at the end of a lifetime, we can do exactly what we have done for the LIGO and Virgo pipes. But we needed to take out the hydrogen that is inside the steel's thickness, that is intrinsic in the production of steel. And so what we did at the end, we did it at the beginning in this case, not the end of a lifetime, but we full vacuum and then baked the pipe at power of 400 centigrade or so, and that got the hydrogen to diffuse out, so we got it all in the pumps. So some will still remain there because it diffuses, and it's clear that things with tritium will get some contamination, but much of it, because tritium is very expensive, much of it can be milked and sold.
Radioactive, that's the
Yes. Oh no, it's radioactive. I mean, it's not. You do this all in vacuum chambers. It's controlled ways. So I totally agree that it is something, but you can milk some, and then it has tritium has a nasty habit of decaying reasonably rapidly. So if it is only tritium, the activation of the steel is a mild problem for storing. And we are going to protect all of the around the reactor. I mean, you said you are for fusion, and reactors produce neutrons, and fusion produce, well, for the same amount of thermal power produced is 43 times more neutrons at 5 times the energy. So there will be much more steel activation problem than from a reactor, except for a reactor, we can stop it completely. Because before the steel, we are going to put a shell, I didn't mention this here, the shell of boron carbide, which is very strong, but it absorbs neutrons like crazy. It gives a little bit more heat, why not? It's negligible, but it's, and that means that the tank outside will see no neutrons. So there will be, apart from the tritium that you mentioned, there will be no activation of the tanks. So apart from the tritium, we would have no worry about radioactivity. Good.
Well, first of all, thank you for your very interesting and comprehensive presentation. You gave also notices about the application potential of your reactor, and that was very interesting. I would like to ask a question. You said that you will be you'll be going to put into the market, into commercial operation in 2028.
Yeah. And well, 26 and 27 is when we have the verification ones, and then let's call it a product. This one will be a pilot plant that will produce one a month. Okay, so that will be 12 a year that will be produced from 28 on. And of course, at the beginning, they will go in the nations that validated them and therefore gave us permission to use them.
So you anticipated my question. My question was, usually there are lab scale plants, then pilot scale plants, then demonstration plants, and then commercial. At which step are you at the moment? I suppose that you have some pilot
the prototype was here and it does not exist anymore. It was disassembled. It was a bigger one, 250 megawatt. And then it was decided to make them smaller because the idea was to bring them in the mine. So we wanted to have total passive safety and etc. etc. And now we are building the production line. So we already are producing fuel. We already are producing fuel cartridges. We already have companies that produce the graphite. We are designing a few parts still, but that is normal in these kind of things. And we expect it to work because a reactor is orders of magnitude easier than an airplane, and nowadays you can model an airplane and it flies. That's what happened with the Airbus 380. There was not that they had to make 3 prototypes. The first one flew and the next one was sold. Okay, close to it. Yes, reactors are much simpler.
It took 1 century to come to the A320. Anyway.
Yes, I think you are correct. But the airplanes were not invented much before the nuclear reactors. In fact, the Orville actually saw the first nuclear bomb to blow up. So the lifetime is about the same. The price of particles that we are using were built in the 60s when I was 4-year-old or 5-year-old. Okay, so the technology is mature. Okay, we don't have to solve too many residual problems, and we have the power of good simulators that allow, and design tools that allow people to build an airplane. And as I said, the reactor is much simpler than an airplane. Yes. Yeah, you are a nasty customer.
Yeah. So the customer first.
No, customer in the sense of fine. Yeah, I say to answer.
Waiting for
How many MMR are you going to buy?
my pocket is very poor in this moment because I come from planes, you know.
Yeah, I know.
So okay, Jokes apart, and waiting for more technical questions from the young.
Yes.
I would go ahead with the deployment model. We have a representative from the political arena, and maybe they would like to understand better how to go to the deployment, reactor time frame, and what else the issues. I will address the question regarding three main points. Normally, whenever you have a new reactor, the thing which is always on the critical path is the fuel and also the associated fuel cycle. But this is not really a problem in this type of reactors. So first question is the fuel already qualified? So if the fuel is already certified somewhere, in which country, and when it will be available to the market, also for, let's say, countries that in this moment don't have a very long tradition in operation of power. So availability of the fuel on the market. I appreciate the fact that you elaborated a lot peculiar features of the fuel, but at the end of the day, the fuel has to be tested, qualified, certified, and licensed by a safety authority, and normal of these things.
Yeah. Of course, the fuel has to be certified. The trial particle has been used and certified himself, have been used and certified for 60 years plus, something like this. Now, the thing is, these cartridges are containment, and they need to be, some of them have been tested already. And then there are other, there are all sorts of studies that and the tests that have been ongoing, mostly at Idaho National Lab. I do not know the details. I asked, that one I really didn't go into detail, that one and another number of points, but I've been asking, okay, this one I understand that makes sense. I mean, does everything else make sense? So that we'll keep a time scale to go critical with the first reactor in 2026. And so far they tell me, yes, we are. There are some doubts, of course, but it seems to be so far so good. Of course, I know that, the devil is in the details. So once you have a reactor almost ready, that is when you will find, oh, I have to fix this, oh, I have to fix that. We are already finding this problem, and so far we are solving them. Yeah, that is a tough question.
A related one, which is again on licensing, also not only the fuel, but the whole reactor to be certified and then licensed. So for that is a non-light water, non-traditional, say, reactor. It's a non-water.
Yes.
So there is the need normally to develop safety regulations specifically. What is the situation of this regulation in the first two countries? You mentioned.
I know that it's ongoing in Canada and it's ongoing in the United States. In fact, it may happen that the first one will happen in the United States, that in Canada, so we may send the first reactor in the other places because of this process that being more slow in this moment in Canada. It may be that these are the things that slow down the process more than the technical issues. And then before you come and ask that, you need the manpower to do that. Now, and you need expert manpower to do all this certification process. Elsewhere, there are a number of knowledgeable people in the United States, in Canada, and there are lots of people that know how to do. Then in Finland, they have a pipeline that when you were at international, well, whatever, international. Yes. You helped organize, so there are people that know how to do that. Some 250 people in stuck with the organization of people of Isaac here.
Yeah, we don't have the trained manpower. However, I was suggesting to our political people that what we have to do is to make a treaty with them and take some of these students behind here, send them over to get trained with them and make the same process for Italy in parallel. And that one will save a lot of time than if we try to train them here on our own, even if we have very expert people in Italy, not only him, we have plenty of expert people here. So
Very final one, you know that this country is very sensitive to the story of nuclear waste management.
yes,
So you showed us that the fuel cycle is 20 years, if I understand.
well, is per cycle. Because when we reuse many of them, we mix them because if we start from 10%, then we can put some 20% mixed with
Depends
burn
on
and stuff.
this, but let's
50
say
years from now, we finally yes.
cycle. So and the concept is a cartridge-based concept.
What?
Cartridge-based. It means that you take the core and you give back to the
Yes.
supply.
We
Can you elaborate a little bit more on this deployment model related to the?
we take everything back at the end. So at the end of a 10-year, or let's call it 10-year cycle, we take the reactor out, put it on the side, put a new one in. Then after a few months, we disassemble everything. And we reuse up to a certain point of the graphite. We reuse each of them as a quote code on top. We know who was where and how long and whatever happened to it. And so which flow of neutron and what was the initial load, all the parameters are there, so we know where to put it the next time. And by the way, it also helps to track them for non-proliferation issues. We know where it is. It's not something fluid like I dissolve the bars in acid, as they do with a zirconium rod. I dissolve them and I got out, oh, I have a missing kilo or something. In this case, this one just does not happen, but that is non-proliferation issue. And at the end of the day, as I said, even after you have exhausted all the useful burnable 235 inside there, of course you don't burn it all, but you burn it partially, then you can either dispose of it or they can be with difficult process. They can be separated, dissolved, even this. And then you can send them for making MOX and being either put back into cartridges like this in our reactors or be burned into fast reactors. But we can make burn MOX at an additional cost, or we can make also the thorium cycle with a lot of modifications. We can.
But the best concept is take back. You give the reactor, and then the supplier take back the whole core, and then it means the core somewhere else.
Yes, it comes back whenever you build it. And by the way, if between other things, because we are proposing, we don't want to just move them around. We want to make like the car companies, that they make the cars more or less where they sell them. So for Europe, we would like to make a supply chain in Europe. Of course, Italy is a very nice place to do that because of a supply chain facility to build up a supply chain. I mean, I visited companies that can do almost all the components, and we can make the ceramic and everything in here as well. But strange thing happens. For example, we wanted to. We thought about making the final assembly in Washington State, and now we change it, and we are going to make this in, oh gosh, Alabama. The weather is much worse, but they made offers that we could not refuse, so we went there. So that may happen also in Europe. I do hope that Italy, that is our best choice, will help us to keep it in Italy, and we will not have to go elsewhere. But these are economically and support-based decision that one has to take when you build a plant. You want to make a plant that produces the stuff in a way that is sustainable economically.
Other questions?
Yes.
Students.
Yeah. Oh. That does not look like a student, that's okay.
Professor, once upon a time I was a student as well.
We never stop being students.
Exactly. I'm still learning. I was curious to learn a little bit more about safety because you're mentioning you are ultra safe, but you didn't really find a way to break the system. But as you're going in front of the regulator, in front of NRC, you're probably postulating some accidents, some possibility of accidents. It's a pressurized system, so you're probably going to have a road ejection. You could have air entrained in the systems, air,
Yes.
and air and graphite at high temperature.
Yeah.
There is oxidations,
Yes.
fire. You have trisoparticles operating at 1300s, you mentioned. And
Cannot happen in our case, but yes, we can, and even if it happens, it is sealed in 2 millimeters, so we can go much higher than
it's true that going back to what we know is that we don't really do anything about trisoparticles above 1500s. So your qualification is you're not going to go above 1500. So I was curious, and going in front of the regulator, why are you telling them what is your worst case scenario?
If you go there and cut the pipe that, when you let in some air going in, you still have a small orifice to go in. And there is a long way to go before you get to the core because it only can burn as fast as air go in. And air that go in also have to come out. So it's not much burning that may happen. And you are only going to burn through for a long time through the neutron shield, neutron reflector, which is so that one is an accident that has a grace period of weeks before you actually get to burn something that then end up to drop not trisoparticles but a cylinder like this to the floor. Yeah. You may have that when you take out the 50-ton cover on top, which is concrete yet thick, and somebody comes in with an high-power rocket that just comes in and blow up everything out of it. Well, first it has to go through a number of layers because there is a steel, and there is the boron carbide, which itself is very hard. Then there is the core reflector, but then if it gets to the neutron reflector, then if it gets to the core, this one is very soft. And so that will absorb the shock wave and go in powder, that will make a fire, but then you just eject the cartridges in the crater, and then you have to go and pick them up with Naruspa and then sieve it so you separate from the dirt, and then you have to do something with them. But it is extremely difficult, especially if it is mixed with something soft that absorbs the shock wave to break one of these. Of course, you can do it if you nuke it, but if you nuke it, who cares about the reactor when a nuke bomb blows right on top of it? I don't think you have to worry about that. Yes.
I'm not worried, but the regulator might.
There will be a lot of questions that they will ask, and one question that was asked is how do you monitor? Who is monitoring these things? And the answer is exactly the way, the same way that you monitor, we monitor the activity in Iran. There are cameras that check it, and so if something happens, you see it. The big difference is that in Iran, they actually disassemble these cameras so they can do what they want without us seeing it. And we make them in, for example, in Italy, there is all interest to keep monitoring it. So nothing bad happens to it. So again, at the end of the day, when you go through the certification process, people have to ask the question. Sometimes you have to suggest the questions and say, look, this one is a nasty question, but this is the answer. And then you have to answer quantitatively the question. And I think that everything that I did think of, and I made it as a game, and I'm not so stupid. I have ideas on how to. I'm creative in producing problems. Before I even thought about working with a company, I made a lot of questions, and I always got convincing answers that I think would convince the regulators. It still takes some time. You have to go through the hoops.
Marco, and then the students.
Yes.
Thank you. Nice talk. Compliment the design because I had it much, as you know. Just a couple of technical questions. You say that the core is, you can change the core, let's say, each 10 years, something
Yes.
like that, 10, 15. How many exchanges you can afford with the vessel? Because others better structure, right?
Yes.
And second question is, which is more or less, if you can say, the working pressure? So the helium
perfect.
is fine again, pressure, more or less.
Working pressure is nominal is 30 atmospheres. Okay. The lifetime we used to say at least three periods. Now we brought it to infinity because we added a layer of boron carbide. So the boron, the problem that he was mentioning is that the steel hardens as you bombard it with neutrons, and then you get a lot of spallation effects into the steel that becomes more and more rigid, and then it can crack. And that is because of proton bombardment. And if we put 40 centimeter of silicon carbide, boron carbide. Now boron has a huge cross-section of neutrons. There are almost no neutrons coming out. So the lifetime of a tank, with a great displeasure of people that build them, will actually be only determined by the lifetime of a technology. People will come with better ideas at some point and will do better stuff. Maybe we'll get to fusion coming out of it. With all of its problems, because fusion have a lot of with neutrons, much more. Because it has, we cannot put the boron carbide around because, well, anyways, I'm not criticizing the competition, but eventually all technical problems can be solved. The lifetime will be essentially infinite there. Yes,
It's time for another couple of questions.
students.
Students,
Yes, sir.
please.
Not the students, but actually finger of the students
Yes.
getting further. So thank you for your presentation. You mentioned the availability of simulation tools, advanced simulation tools. This is of course true for many things in nuclear, but I personally work on the modeling of nuclear fuel. Your fuel seems amazingly complicated to model with available tools. So I don't know what tools do you have in mind, what tools are currently developing?
I'm not an expert, but a few years ago, well, many years ago, I happened to work and supervise a guy that now is the director of Nuclear France, and he was simulating things with Géant. Now, that is what for high energy physics. And at the time, yes, you make a simulation of the detail, but then out of the detail, you make a homogeneous equivalent, okay? And with that, now the next step of a simulation is much simpler. So it's all how much good cells, common cells you use when you use your simulation. I don't know which simulation tools are used for reactors. They certainly are not Géant, or maybe they are, I don't know. But the problem is always the same. How intelligently do you use your simulator to do that? Marco, do you agree on my answer?
I understand the problems, the concern by Davide, because I know that the issue about modeling fuel is
I know.
very tough.
And we never use nothing.
Yes, exactly. Together with experiments, I think that.
And experiments, yes. You need a computation of the simulation every single step. But that one we know how to do it done in the past. So, and much of these tests have been done. There is a lot of tests that were made in the international lab that is dedicated to this sort of tests. And so I think that is mature enough that we can design the airplane and it will fly as we expect it to fly.
However, just to give an information, the IAEA normally doesn't deal with nuclear codes because of the OECD, NEA, and the RC is doing. However, for the gas-cooled section, the IAEA has collected all the simulation tools developed in Germany for the program. For this one, this set of codes also for safety code and fuel is available to member states. So very interested. We can approach the IAEA.
And I'm sure that EIA also requires a lot of validation of the code before, yes.
Particularly for that fuel, which
So
never designed. It's not only TRISO, it's a particular TRISO application.
absolutely, yes. Once more from the students. Real student.
If not, okay, let me ask you a question, because one of my two questions was already asked by Stefan, was about licensing process. You mentioned generation 4. 2 out of the 4 key pillars of the idea of generation 4 are waste minimization and waste burning. It seems to me, but please correct me, that your solution is not really very interested in this type of two items, because reprocessing with this type of fuel, you mentioned, is almost impossible. I'm not saying impossible because you can do everything.
Yes, it can be done.
But it's not the best, not more type of fuel that we may think about if we want to reprocess and then to burn the nuclear waste. And the second is about waste minimization, because all the nuclear reactor that you show us, we should manage as a high-level waste at the end for the disposal, because, and you know that we have not yet found a solution for the graphite disposal in the world. There are several initiatives. Italy is also involved in these issues with Sogin, with other universities, with Enea and other bodies. But okay, I think that the plus of the design that you presented probably are more than outweigh the two critical issues about waste minimization and waste burning. And is that true, or are you thinking about probably other brilliant solutions on those two?
The waste, yeah, there are first thing, we can work between 5 and 20% of 235, and we can play with the shape, the distribution of higher density, lower density outside and inside to keep burning. So if we start from, not available now, but will be available soon, the 20%, but then you can burn more efficiently. And that is limited, is roughly equal for every reactor that you want to do. And by playing this, I reuse it, not recycle, I reuse it until it's burned out to the limit. We minimize the amount of. Now, the cartridge, the graphite also can be reused. And because we are running at high temperature, we are in the self-healing regime, so the graphite lasts much longer than if you run graphite at low temperature, as for example, done in Chernobyl and in some of the older, now dismissed reactors. So the amount of waste is reduced dramatically. In the sense that the reuse cycle is multiple, and so we can go and reuse a number of times. The other material that is polluted is, if you don't put the neutron shield, is the steel. However, as I said, is we will put the heat, the neutron trap outside, the boron carbide borons. And so the steel outside will get very little or negligible neutron activation. So we are reducing a lot of these things. And if you don't want to retreat them at the end, these things, these are the most dangerous part. The graphite is much less, no matter what you may say. Obviously, you agree on this point. There is a brilliant solution that people are studying now. And normally what you do, you build a tunnel, you go down half a kilometer, and then you put the stuff there and you leave it there. And it's half a kilometer. But the solution that is being considered now is to make a 5-kilometer borehole down, and you throw down some concrete and cartridges down there, and then you make half a kilometer out there, and then you come back, and you know, because of fracking, you know, you can make directional drilling, so you can make many holes side by side, each about half a kilometer deep. Then you refill everything with concrete, and now you have a shielding which, instead of being if you are 200 or 300 meters to have maybe a possibility of having a water table problem there, you are much deeper. If you go deep enough, there is no water, just because the water just comes out of it. And so people are considering this, and it can be done with other vitrified or ceramicized spent fuel, not only our, but in our case, we don't need to do anything. It's ready to go. So that one is a new brilliant solution. I mean, you can have others, but that's it.
Thank you very much. We reached the limit of our time for the meeting. I want to thank, first of all, Riccardo for the brilliant seminar. I go to the I want also to thank you for attending, and let me have a special thank to the two members of parliament that join us today. It's not an automatic, it's not a normal event. Yes, for attending the World Seminar, it means that it is a clear signal that the political side is really looking in a serious way at that topic. It's a very delicate topic. It's not an easy topic, especially from the political point of view. So it means that there is a new new interest, new way to think about critical problems for our country, our continent, and our world. And energy is one of them.
Yes, and if you allow me one more few seconds to mention this, there was a parliamentary motion that passed something like 185 yeah and 45 no, that essentially charged the government to go ahead towards the reintroduction of energy, of nuclear energy.
Thank you very much.
Nuclear energy in Italy, so that is the first step. And then Senator Potenti, that just walked out, and organized, wanted it here for a few seconds more, has organized a audit, Senate audit, audition, in which I'm scheduled to go and present these things to help further the path of nuclear in this direction. Unfortunately, it has been delayed by first emergenza siccità, then emergenza flooding, and then emergenza bridge. And so I keep getting delayed, but I expect that in a week or two this will happen. And oh, you are coming back. You heard that I was talking about you. So I just came to make a photo. And finally, there will be another happening in a couple of months at the chamber again that Honorable Squarey is organizing in any case. So there is a lot of activities that we are doing to educate other parliament people, and then we are planning to push for the press to give information that educate people. Even before that, we commissioned a poll of people, and it turned out that there is a majority of Italians today that is favorable to nuclear, and if it is small and safer, it goes up to about 60% majority, which this one will be will go to the papers soon, but I give you a preview of these results.
Well, we can confirm that the interest from the young generations is pretty high, with no ideologic approach. Very interested in the environmental issues, in the energy issues, in the security, in the economy. So we can testify that the number of students that are interested in such an issue, including nuclear, is growing fast, and Polytechnico will be available to share information about these new technologies. There are several initiatives today going on in the world, in Europe, and also in Italy. So please stay tuned and see you soon. Thank you.
Very good at, the young people are very good at smelling the wind. There is not yet a nuclear power, but you already got twice the new students last year.
Yes, Polytech, but also the other universities that are in the certain consortium in Italy, involved in nuclear, Polytechnic di Torino, University of Bologna, University of Pisa, University of Roma Sapienza, University of Palermo, together with Padua. They are experiencing the same interest, growing very fast. So again, thank you very much.
You have the time and see this stop for a few minutes, then I put them back into my suitcase.